Yeah. Is my screen visible? Siddhartha, could you please confirm?
Yes, ma'am.
Yeah, okay. Good evening, everyone. I'm Vanniya doing my PhD in photonic metasurfaces under the guidance of Dr. 𝐒𝐬𝐬𝐬𝐬𝐢. First of all, thank you all for joining. I'm really glad to have opportunity to speak with you all guys today. In this session, we'll be exploring something exciting like how to design meta surfaces in COMSOL multiphysics software. Whether you are new to meta surfaces or looking to strengthen your simulation skills, this talk is designed to give you both the physical insights as well as practical tools needed to just get started. So first, why meta surfaces and as a camera module, right? And it is not made of a single lens. Rather, it's a stack of lens arranged. So it typically has a thickness of around 4 to 8 mm. So now imagine what if we have a ultra thin, sleek, like high resolution and less aberration in a very much smaller space, like very much less than 1 mm. That sounds interesting, right? So here comes the first application, that is meta lens. They are made of nanostructures, which you can see here. And these can precisely control the light which is hitting on that surface at sub-wavelength scales. So these are ultra thin and these are flat and these are very light in weight, and we can use them not only in our mobile phones, but we can replace the bulky lens in the augmented reality glasses, and we can also use them in the microscopes we use in our lab in order to achieve ultra compactness, so that could fit on a chip. The next fascinating application is metasurface holography. The traditional holography, they capture light interferences using bulky optics and photosensitive materials. But with the meta surfaces, we can design holograms using these nanoscale elements. We can modify the phase of the light that is interacting with our meta surface, and we can project very complex 3D images. And another exciting capability of metasurface is polarization conversion. So a polarization converter is actually a device which can convert a linearly polarized light into a differently polarized light. The traditional polarization converters like quarter wave retarder, half wave retarder. They use birefringent materials that have different refractive indices across different axes. So they are very bulky, and we also have material limitations, and they only have narrow band. Meta surfaces like are very ultra thin. For example, if you see here, if you send a linearly polarized light on the meta surface, when it comes out of this meta surface, you will get a circularly polarized or elliptically polarized light. So this is also one of the fascinating application of meta surface. And the most imaginative application of meta surfaces is clocking. Making things invisible. You all might have watched this in the movie Harry Potter, right? But that style of invisibility is still a challenge. But meta surfaces offer a very real physics based approach to clocking. So by engineering the phase response of the metasurface, we can make light behave as it never interacted with the object, and you can hide the object inside surrounded by the metasurface. So the object becomes optically invisible, which are used in defense applications. And the practical applications of metasurfaces is sensing. So conventionally, sensors rely on bulky optical elements to detect the changes in the surrounding environment. Like it depends on bulk optical elements to detect the changes in wavelength or polarization or light intensity. But metasurfaces being ultra thin, they can detect even a very tiny change, like the change in the temperature in the surrounding medium or change in the gas concentration. So these can be used in various applications like refractive index sensing or environment sensing, a detection of gases which are very harmful, and so these are ideal applications for label-free and ultra-compact sensing platforms. And the other application is metasurface absorber. So as I said, metasurfaces are arrays of subwavelength nanostructures called meta-atoms. So why meta-atoms? So natural materials, they are made of atoms. And similarly, these meta-surfaces are made of meta-atoms. So these meta-surfaces are 2D counterparts of metamaterials through which you can manipulate the phase, amplitude, frequency, and polarization of the EM waves hitting on the surface. So these photonic metasurfaces operate at optical frequencies, radio frequencies, and microwave frequencies. And here we are looking on photonic metasurfaces, which can manipulate light at specific wavelengths. And distinctive optical properties can be obtained by varying the shape of the individual atoms. Here it is cylindrical. We can vary the shape like square shaped or rectangular shape. And by varying the geometry and by the material which it is made up of, you can achieve different optical properties. So there are three types of metasurfaces, photonic metasurfaces, namely plasmonic metasurfaces, dielectric metasurfaces, and hybrid metasurfaces. So the first type is plasmonic metasurfaces. So they are made of metals. The meta atom is made of metals like aluminum, gold, and silver. So they work on the principle of surface plasmon resonance, so which is caused due to the oscillation of free electrons in the meta atoms. So the advantages of using these plasmonic metasurfaces is like they have a high field confinement inside the meta atom, and they also have a high sensitivity. But it also has this disadvantages like there is high loss if we go for plasmonic metasurface. So the second type of metasurface is dielectric metasurfaces, where we use high index dielectric materials like silicon, titanium oxide, or gallium nitride. So this works on the principle of Mie resonance. So Mie resonance happens whenever the dimension of the meta atom is very much lesser than the wavelength which is incidenting on the meta atom. So here you can achieve a high quality factor, and the cost is also very less, and the loss is also very less when we compare it with its counterpart plasmonic metasurfaces. But the disadvantage is like very less field enhancement, and it is also sensitive to the angle of incidence of the light. And the third type of metasurface is hybrid metasurface, which is a combination of both plasmonic and dielectric materials. Here you can achieve high field enhancement, high directivity, low loss, and low cost. However, the fabrication is quite challenging. So in this session, we'll design a metasurface unit cell with the following dimensions. So the meta here, you will have a substrate made of silicon dioxide, and the meta atom will be made of silicon, and the background medium will be air. So the dimensions, The height of this meta atom is 220 nanometer and the width and depth are 570 nanometer. Uh, so already we have launched the COMSOL multiphysics software, and this is where the design begins. So let's start step by step. So first, we need to click on the model wizard. This model wizard would be great if you need any guided setup, and if you are doing multi-plant model. So now I'm going with this model wizard. Then click on 3D. You can also work in 2D or 2D axis symmetric. But 3D gives us full picture of light matter interaction. So select 3D. And now we need to choose the physics we are dealing with. Since we are going to study how light interacts with nanostructures, we go to optics and then wave optics module. And then here we have four different options. And we need to go with electromagnetic waves, frequency domain, and then add, and then steady. So now we need to select steady. So here we have different options. We'll choose wavelength domain. So this allows us to simulate how the structure responds to different wavelengths. So it will be perfect for plotting the transmission spectrum. So now I have chosen the steady. So done. So that we have our setup model ready, and this is the console interface. So on the left side, we have model builder, and where you will have global definitions, component, steady, and results. And in the middle, we have settings window. On the right, we have graphics window, where you will see the geometry or the field plots or the simulation results here. And at the bottom, we have messages. So first, let me click on this geometry, and we are going to work in everything in nanometer scale. So I'm going to change this to nanometer. And then I'm right clicking on this, and we have different options. Like I'm going to create a substrate, which is going to be a block, and I'm naming that as substrate. So now the width of the substrate is going to be 700 nanometer. The depth is also going to be 700 nanometer, and the height of the substrate is going to be 500 nanometer. Now, if you click on this build on objects, this will get built. So this is the position. So the base of the block is at the corner, which is located at the 0, 0, 0 in the coordinate axis. So now our substrate is ready. Next, so this is going to be our meta atom. So the width of the meta atom is going to be 570 nanometer, and the depth is also going to be 570, and the height is going to be 220. So now if I build on objects, so you could see here the meta atom has been built here. So it is at the bottom. Now we need to choose the Z position as 500 nanometers so that it will go at the top. Again, it is not at the center. So now we need to position that at the center. For that, I'm changing the X and Y to 65 nanometer. So if I build, now it is at the center. So the next step is we are going to build the background medium, which can be anything. Now I'm considering air as the background. So again, the width is going to be 700 nanometer, depth is going to be 700, and the height of the background is going to be 500. I'm considering these dimensions. If I build, so it got built but down here. Now I need to position it to top of this. So 500. So if I again build this, now I'm enabling this transparency so that you could see clearly. So this is all about the geometry. Now we need to assign materials to the geometry. So I'm clicking on materials. So you have various materials available here in this material window. Now I'm choosing the substrate. The substrate is going to be silicon dioxide. If I double click on that, it will get added here. And we need to choose the domain which is going to be substrate. So this is going to be our substrate. So I'm just removing all the other things. So one, this is going to be the silicon. And next here you could see this X mark. So once you add all the materials, that will go away. So again, our meta atom is going to be silicon. So I'm double clicking on that. It got added here. And so this our meta atoms and relating it. So this is going to be our meta atom, which is silicon. And now this background medium is going to be air. So I'm going to assign air to the background medium. So this is not air, this is air, and this is meta atom and relating it. So now that we have assigned all the materials and this into mark went away. And the next step is this study, which is EWFD. Now we need to assign the ports. So I'm right clicking on this EWFD and then port. So we are going to assign the input and output ports. So this is going to be our input port. So here we need to choose the type of port. It is going to be periodic port since it is going to get repeated along the X and the Y axis. And the wave excitation at this port is going to be on, and the port input power is 1 watt. And we are using the electric field, which is Y-polarized. So this is going to be 1 volt per meter. And then we have to assign the output port. So again, I'm right clicking on that and port. So now this bottom is going to be our output port where we'll measure the transmission and reflection spectrum. So here, the type of port is again going to be periodic, and wave excitation at this port will be off. And the output also will have the Y-polarized electric field. So I'm changing this to 1. Now, this is a meta-surface unit cell. Now we are going to give the periodic condition so that it will get repeated on the X and Y axis. So we'll have arrays of meta atoms. So right click on this EWFD and then you have periodic conditions. First, let us assign the periodic condition along the X axis. So this is going to be periodic condition. We can change the conditions also. The next step is, so you have two different kinds of mesh. One is user control mesh and the other is physics control mesh. So now we'll go with physics control mesh. And we have different element size options like extremely coarse to extremely fine. So depending on the mesh size. So now we'll go for normal. We can also go for extremely fine, but if normal accurate result, then you can go for normal, or else you can go for extremely fine. So now I'm going for normal, and I'm building the mesh. So the mesh got built, and the next step, the final step is the study. So where we are going to study in wavelength domain, and the wavelength is in micrometer. We are going to study this in near infrared region. So I'm going to choose the wavelengths starting from 1.4 micrometer to 1.6 micrometer rotation time. We can also reduce that to 0.001 for getting high resolution. So now I'm replacing this, and everything is done. And now I'm going to compute. So it may take, so now the simulation is done. Now we are going to observe the results. So by default, this EWFD study plots the reflectance, transmittance, and this is actually the can also view the animation, how it is getting transferred. And normally, when resonances or short dips or peaks in the spectrum. So now we are going to look at the spectrum. So this is reflectance, transmittance, and absorptance spectrum. I think here you could clearly see the blue curve represents the reflectance, and the green curve represents the transmittance. So transmittance is nothing but how much fraction of incident light power that passes through the material. So it is basically the ratio of the transmitted power to the incident power. And so we are getting a dip around this 1.47 micrometer. So here the transmittance is a zero, which means the light getting hitted at this wavelength is completely getting reflected. So you can use this spectrum for various applications. Like here we have assigned the background medium as air. So now if we keep a different background medium instead of this air, if we so you will get a different spectrum. You will observe a shift in the spectrum, shift in the wavelength of the transmittance curve, which can be used in sensing applications. So this is all about the reflectance and transmittance plot. And there are other project ideas you can explore, like metasurfaces for beam steering and design of metasurface observers, and design of tunable or active metasurfaces. And we can also design metasurface sensors for biomedical applications. So if you are really interested in learning this COMSOL software, then you can visit this COMSOL Learning Center where you'll find like plenty of video tutorials on COMSOL multiphysics. You can also scan this. And about the career prospects, this COMSOL is highly used in academic research purpose, and it is also used in industry, and you'll get PhD opportunities, and you find career opportunities in energy sectors, biomedical, electronics, aerospace, and automotive field, and also enhances your academic profile. So that brings us to the end of today's session. So we have seen how metasurfaces can control light in powerful ways. You can ask me. Any questions? No questions? Do you guys understand anything?
Maybe a little.
Maybe a little. Okay. So what about others? So in our lab, we are working on fiber optic sensors like fiber Bragg gratings, and also we are working on photonic metasurfaces. And we have facilities of using two different softwares like COMSOL Multiphysics and Opti System. So you can utilize all those facilities that is available in our lab, sensing with photonics and optics laboratory. You can also visit 508C to see all the experiments which are carried out in our lab. And these are the links you can connect with the Optica student chapter. You can scan these QR codes if you're really interested to be part of this Optica student chapter. And thank you so much, guys, for joining. Okay, so Vinay is asking some questions. So can you explain a bit about boundary conditions for different applications like active metasurfaces? So we have different boundary conditions like scattering boundary conditions, impedance boundary conditions, transition boundary conditions, and for plasmonic metasurfaces, people usually go for this transition boundary conditions and impedance boundary conditions. So if you are working on scattering applications, like if you're analyzing the scattering applications like knee scattering, then we'll go for scattering boundary conditions specifically for spherical nanoparticles. And usually for periodic structures like this, we'll go for periodic conditions in COMSOL multiphysics software. And if you are going for single metasurface unit cell, people also go for this. So, any other doubts? Vinay, are you clear? Okay.
Can you explain once about the selection of three layers now?
Yeah. So, a selection of three layers. So, first, we'll create a geometry, and then a selection of three layers. In the sense, you are talking about the domain selection.
Yes, ma'am.
So, here you can, yeah, so here you have two options, optical or non-optical. domains. So, if you, for example, I have assigned this silicon dioxide only for this. So you have two options to do this. The first way is manual. So manually you can or else you can go for all domains. And here already we have assigned the silicon and add. So it is appearing like overridden. So it will automatically assume one as if you're going for manual, first let me delete this. So now I have chosen manual. I'll choose this. And then now I want SI. SI is our meta atom, but I can't select that by this way. So now I need to hide this. So here you have an option to hide. So this is click and hide. So if you click on this and if you hide, so now you can select your meta atom to be silicon. Now again to view all these things, you have this other option view unhidden. Sorry, so you have view all options here. So now you can choose the add in this way. The I think you're clear now for this. Any other doubts on the simulation part or about the applications of metasurfaces?
I will try it in Akka. If there's any problem, I will
Okay, sure.
I'll
Okay, guys. Thank you so much for joining. Bye.